Hi everyone, welcome to this webinar dedicated to commercial aviation. I'm really happy to be there with you. I hope you're all well. So during a bit less than 1 hour, I will have the pleasure to present you the challenges of commercial aviation in the scope of a large-scale rollout. So of course, like other webinars you attended, you will have the opportunity to ask your questions in the chat box on the right side of your screen. So while we are waiting for the latest attendees to connect, I will ask you a first tricky question. You'll be able to answer that question in the chat box as well. So here's the question. When do you think the first hydrogen-propelled flight will happen? When do you think the first hydrogen-propelled flight will happen? You can start writing your answers in the chat box right now, and we'll wait and start in about a minute so that everyone's connected. It's 11:01. Let's wait one more minute. A reminder of the question I've asked. When do you think the first hydrogen-propelled flight will happen? Answer in the chat box, and I will give you the right answer a bit shortly after the beginning of the webinar. One more minute so that everyone is connected, and we'll start. Okay, let's start. Hi everyone, I am Nicolas Huygeveld, Managing Partner North America at IAC Partners and member of the Aerospace and Defense practice at IAC Partners. I'm very delighted to host you for this webinar, and our discussion, this webinar, and your questions will be moderated by Frank Garuzzo, one of our senior consultants here in North America at IAC Partners. So during this webinar, I will have the chance to share with you the possible use cases of hydrogen aviation and the main challenges for hydrogen aviation to be rolled out on a large scale all over the world. So after this, the agenda for today, after an introductory overview of the different technologies in competition with hydrogen to reduce carbon emission, of course, we'll deep dive into these challenges and the possible use cases for hydrogen aviation. So there will be 40 minutes of presentation and 10 minutes for a Q&A session at the end. So don't forget, write all your questions in the chat box, and our moderator, Frank, will pass them along to me so that I can answer some of them at the end of the webinar. So I've asked a question at the very beginning. When do you think the first hydrogen-propelled flight will happen? The answer. Of course, there was a catch in the question, because this aircraft already existed. Indeed, the Russians, back in the 80s, some 32 years ago exactly, they've modified a Tu154, Tu154, which was a typical regional aircraft back in the days, to make it a Tu155 with one out of the engine modified to run with liquid hydrogen or liquid natural gas. So this plane made some demonstration flights, about 100 flights, at least 5 of them with liquid hydrogen and the other ones with liquid natural gas. So you see, it's not science fiction. This page and this question is to show that it's a proof it can exist. It's not science fiction. It was, of course, not a commercial flight. It was not with passengers, but it's doable. It's clearly doable. Let's have a look now to the landscape of the different technologies in competition with hydrogen when we talk about reducing the carbon emission. So there are four categories of technologies that we will go through. First, batteries. So clearly, batteries is not a viable solution for commercial aviation. It's mainly due to the low energy density of batteries. And you will see in the quote of the CTO of Airbus on the left side of your screen that the impact on the payload and on the operating range of a Boeing 737 or Airbus 320 will be too high to consider it possible for commercial aviation. It purely doesn't work due to this low energy density. Second category, you've got the Efuels or synthesized kerosene. Pretty interesting solution, interesting technologies, because it has exactly the same characteristic as the current kerosene. So you don't need to modify the aircraft, the engine, to run an aircraft, a commercial aircraft with synthesized kerosene or e-fuels. It's made out of carbon, hydrogen production via electrolysis, and you need also some energy to manufacture these e-fuels. The only drawback is the very high expensive cost to produce these e-fuels. Currently, it's estimated at around 10 times the cost of production for the kerosene. It's already approved by the FAA, so that's a really promising thing, and they can use it up to 50% as a propellant. Fuel cells, third category, is made out of liquid hydrogen. So fuel cells can be viable for aviation, but only for very small aircraft. Very small aircraft, because of the weight penalty to onboard fuel cells on an aircraft. You have some figures in the quote as well. If you would want to use fuel cells to propel an Embraer 175, which is a 80-passenger aircraft, we would need to increase the propulsion system from 2 tons to 20 tons. So knowing that the maximum is 40 tons, it clearly doesn't make sense for such an aircraft. It's too heavy, but it has some interesting application, and we'll see that later on. And finally, last, liquid hydrogen used as a propellant. It's, to our knowledge, the unique viable technology to operate commercial flights for mid-long range aircraft. It has, of course, its advantages and disadvantages in various criteria. One of them being that it takes much more space than the current kerosene, and it has cost impact, etc. We'll go through that. Let's have a look at the different application of hydrogen in the industry and their maturity level. So on this graph, you have on the left side the TRL maturity scale, technology readiness level. It's a maturity scale from 1 to 9, 9 being the best maturity level. And in columns, you have 4 categories of application of hydrogen. So you see, starting from the left, from the industry application, that hydrogen is very old. The petrochemical industry is already using it for centuries, essentially to manufacture fertilizers, ammonia, this kind of stuff. So we will not deep dive in it, but keep in mind it's something that it's well known. Maturity level number 9, of course. Lately, 3 new applications appeared using hydrogen. First, grid balance. Grid balance, the principle here is that you use hydrogen to store the energy produced by a source of energy. Could be, for example, wind turbines. And depending on the need, for example, during a peak in consumption or during the night, you will re-inject this energy into the grid to provide electricity to the network. So it's already existing. It's already in place. It's at a good maturity level. Following category, heating. Heating, the principle here consists in boosting the gas network of a city with some hydrogen from 10 to theoretically 20%. It's greener this way. The gas network is much greener, and it enables to heat some commercial buildings, malls, and some home appliances applications too. And last, mobility. Mobility is at the front line of hydrogen usage lately in the last years as well. So let's start from the top with the TRL level number 9. You see buses, cars, forklifts. They already exist using hydrogen. There are hundreds of buses operating with hydrogen all over the world. At least 15,000 cars operating with hydrogen as well. The first one was produced by Honda some 18 years ago. Yeah, 2002. You've got right under it the trains and the trucks. Trains, very interesting and promising application of hydrogen as well. There is already an Alstom train in operation in Germany for 18 months now, operating only with hydrogen. And trucks are coming also as a mobility mean, using hydrogen as fuel, basically. We'll talk about that later. And then you have aviation. For aviation, you have 2 categories mainly. The propeller aircraft that we position at TRL level number 6, meaning that there are some prototypes already. We'll see how and the use cases are done. And you've got the jet aircraft, the mid-long range jet aircraft. Depending on who you talk to, what kind of experts, and depending on the studies, the TRL level for jet aircraft is positioned between 2 and 6. So we've decided to put it at level 4. So clearly this plane doesn't exist. It's not mature. It's not ready yet. Hydrogen is at the top line, at the front line of the latest news. You've seen that probably if you are connected today. And most of the relevant countries all around the world, they have decided to release some major investment plan to promote the use of hydrogen in the global ecosystem. So some funny facts or interesting facts in North America, in US, for example, there are no real major public investment or announcement around hydrogen. It's mainly a private investment. We can quote the example of Nikola Trucks, manufacturer of electrical and hydrogen trucks. They've raised some $600 million lately to build their production plants in Arizona, and their market cap is already higher than Ford and FCA. So it's promising, even if the trucks are not existing yet. In France, the example of this 1.5 billion euros investment is interesting because it's purely dedicated to aviation. It's not only for the general usage of hydrogen in the industrial ecosystem. So they expect to see the first prototypes in the next 6-8 years and to have a carbon neutral aircraft by 2035. That's the plan. So this page is to show you that it's a multi-billion topic, and there are a lot of major investment done in most of the relevant countries. Let's switch to the use cases of hydrogen in civil aviation. So we've positioned three major steps of possible use cases and with associated timelines. We'll start with synthesized kerosene or e-fuels. We briefly talked about that. They're interesting because they have the same characteristics as the current kerosene. No need to modify the aircraft, no need to modify the engine, already approved by the FAA. So according to us, on the short mid-term, so 2025, 2030, despite of its more expensive cost of production, we could see some aircraft operating with e-fuels. Lufthansa, for example, they have already started in Hamburg to prepare themselves to operate some aircraft with this kind of e-fuels, and it's a promising one if the production of it is well done, is done in a green way, meaning that the carbon is captured in the air to produce these e-fuels. So it could be greener and operating with hydrogen. Cost impact, clearly. We do not see before 2030 some application using fuel cells. And these applications of fuel cells will be mainly as a power supply in substitution of some auxiliary power unit already existing in the aircraft. You remember there is a big weight penalty using fuel cells, but we can expect some greener aviation, slightly greener aviation with fuel cells onboarded on the aircraft in substitution of some auxiliary power unit, anti-ice, APU, and this kind of systems. And according to us, we do not expect hydrogen, liquid hydrogen, or e-fuels as a propellant before 2040, with application on a small propeller aircraft with fuel cells. Sorry, it's not e-fuels, fuel cells for propeller aircraft, with the constraints that you need a redesign of these aircraft, and liquid hydrogen as a propulsion mean for commercial aircraft. So it's not going to happen before 2040s, according to us, even if, for example, France wants to have the first one in 2035. We'll tell you what and why. So first, we have these two categories of aircraft: propeller aircraft and jet aircraft, and we've positioned them on a map, on a graph, with two major scale: the number of passengers vertically, which reflects the size of the plane, and the operating range of the aircraft, whether it's a propeller or a jet aircraft. And we will see what are the possible use cases depending on the aircraft. So considering the e-fuels, the fuel cells, sorry, considering the e-fuels as a greener mean to propel some aircraft, the application of these fuel cells, sorry, is limited by two major factors. So you have this weight penalty that we've talked about, that will prevent you and the commercial aviation to use it to planes bigger than 20 passengers, more or less. And also the limitation on the speed of the propeller, which is with the speed of the plane due to the propeller, which is impacting a lot the operating range possible with using fuel cells. And then, depending on, of course, of these speed requirements, there is this striped area where there is a trade-off to be done if fuel cells are viable, or if we have to use clearly liquid hydrogen to cover this area. Liquid hydrogen, once again, seen according to us as the unique viable solution to be applied for commercial aviation with a long operating range and aircraft as big as we see today. There's a frontier that is moving, of course, and this frontier is depending on the speed requirements to be able to operate on the long range. And it's the only technology that we see as enabling to offset the weight or volume ratio of the current kerosene and the fuel cells, of course. So let's have a look at the different prerequisites to a large-scale rollout of hydrogen aviation. Four main challenges for large-scale hydrogen aviation. You have in mind so far that the aircraft quite logically needs to be redesigned so that they are compatible and compliant with the usage of hydrogen. Of course, a lot of systems need to be developed. The aircraft will need to be certified to fly with hydrogen. A lot of challenges, but there are three other ones. Following ones being the cost impact. We'll see that to get lower emission of carbon, you need some more money to produce the hydrogen. So there's a challenge to overcome here. Electricity production. If we put ourselves in the scenario of a large-scale rollout of hydrogen aviation, we would need to produce a big amount of electricity to run the electrolysis necessary for the production of hydrogen. And if we want to fully hydrogenize the commercial aviation, we would need to increase 35% the production of electricity globally. So that's a major move. We'll see what it represents. Hundreds of nuclear plants, of course. Last challenge, the supply chain. Even if you are able to produce the necessary required amount of electricity, which is something doable, technically doable, you would need to store this energy and deliver this hydrogen to all the infrastructure, the aerospace infrastructure all over the world. So we talk about roughly 40,000 airports all around the world. And switching from kerosene to hydrogen will take time. It's not a small move. It's not happening overnight. So a lot of challenges to overcome. Let's deep dive. So first challenge is to make the aircraft compatible, let's say, with the use of hydrogen as a propellant. So a lot of impacts on various systems, on the engine, on the frame of the aircraft, sorry, various valves and management of the propellant. And one major change that you see with the color pink and blue on the planes, on the aircraft. Currently, we store the kerosene in the wings of an aircraft, but due to the ideal shape, which is cylindrical to store the hydrogen, we would need to put it somewhere else than in the wings. It's not possible to have this hydrogen, these cylindrical tanks, hydrogen tanks in the wings. So the major concepts so far, the main concepts are with the tanks of hydrogen on top of the passenger cabins, so that it evaporates above the plane. So major change in terms of design. Lot of work to validate and to get a good maturity level on this change and get a certified plane ready. Next challenge, the cost. We want to use hydrogen to reduce the carbon emission. There are three different kind of way to produce hydrogen and to produce three different kind of hydrogen. The thermochemical conversion, the oldest one. With this one, you can produce what we call commonly called gray hydrogen, the one used by petrochemical industry. It's made out of fossil fuels, so clearly it's not green in the sense that it emits a lot of carbon in the air. And then lately, two other kinds of hydrogen appeared, the blue hydrogen and the green hydrogen. The green hydrogen is clearly the target. It is made out of electrolysis, and the energy is provided by renewable sources. So it's clearly the greener one, that's the target, biochemical conversion, production mean. And in between gray and green, you have the blue one with two subcategories, the grayish one, which is fossil fuels with carbon capture and storage system, and a greener one, which is like the green one, made out of electrolysis, but the energy coming from the grid and not renewable sources. So we'll see in the next page the different impact on carbon emission and the different cost impact as well of these three kinds of hydrogen. So on this graph, the gray bar represents the amount of carbon emitted to bring to the plane a certain amount of energy. From well to wheel, you can say it this way. So the baseline is kerosene, clearly. On the left side, currently you need 12 kilograms, you emit 12 kilograms of CO2 to bring a certain amount of energy to the aircraft. And quite funnily, we already see that the gray hydrogen is not green, because it not greener. It emits more carbon than the current kerosene, and it has a ticket a cost increase of about 8% in comparison with the current kerosene. So the production cost is higher and it pollutes more. So not the future, clearly. And on the right side of the screen, you have the green hydrogen, the target, with very few carbon emission, but a big disadvantage is the current production cost is 20% higher. So one of the challenges is clearly to offset and to find the ways and the levers to reduce this cost impact so that it's not supported by the passenger on the ticket price. So in the end, currently you have to choose to be green or cheap. It's clearly a trade-off. It's not a black and white choice to make, and there is still a lot of work to do to get both advantage, being green and being cheap, or at least not more expensive than current kerosene. Following challenge, electricity production. We mentioned earlier that to switch to a complete hydrogen and commercial aviation, we would need a 35% increase in the electricity production. To illustrate that, we took the assumption that Atlanta Airport, one of the biggest airports all around the world, with 1,200 takeoffs a day, switched to hydrogen aviation. Currently, you need 7,200 tons of kerosene per day for Atlanta Airport. So the equivalent amount of hydrogen would be 2,600 tons of hydrogen needed per day. And to produce these 2,600 tons of hydrogen, you need 6.5 gigawatts of energy. What does that represent, this 6.5 gigawatts? If we consider nuclear technology, we talk about 4 nuclear plants of 1.65 gigawatts. So it's knowing the timeline and the difficulty and the big investment. We talk about $60 billion investment to get a nuclear plant, an EPR reactor. It's only for Atlanta Airport we're talking, so it's a big move. If we consider another technology, a greener one like solar panel, to get these 6.5 gigawatts produced, you would need 87 million of solar panels associated with $50 billion investment. So lots of investments, lots of job to do to transform Atlanta Airport, only one of the biggest one, but not the only one, into a hydrogen airport. Last challenge on the supply chain. On the supply chain side, you see on this graph that it's going from hydrogen production with various production means, technology, thermochemical, electrolysis, biochemical conversion, various ways to condition the hydrogen, compression, liquefaction, absorption, up to the dispensing and the application. So it's a complex various alternatives in terms of supply chain. If you're interested, we've established the different cost model for this supply chain, and depending on the use case you target, so the advantages and the cost impact, of course. All the players of energy are trying to position themselves on this supply chain, and they all have very different views on where the value is and where they should be positioned to capture as much value as possible and generate as much revenue as possible. And depending on their activity, their business, it could be a defensive move. For example, Total, historical and global gas producer, sees hydrogen as a threat for them. Clearly, they have a know-how for gas production, and they have the gas station network. Could be a good thing for the future for hydrogen, but they see hydrogen clearly as a threat. In industrial specialists like Air Liquide, they have the knowledge to produce and distribute this gas. They see it as a potential, let's say, alternatives and other offer they could have in their portfolio, and they are also looking for the right place to be on the supply chain to propose the best value for the future ecosystem of hydrogen. Some utility providers like ENGIE, they see hydrogen as a great opportunity for them to benefit from a lot of synergies with their current business, knowing that they have the green source energy. So it's clearly a promising future for them. And lastly, you have the equipment manufacturers. They have the production means, they have the technical solutions, and they are also looking for the right place to be on the supply chain to capture as much value as possible and to generate as much revenue as possible. So all in all, you see that the supply chain is not mature yet. It's moving. There are some trials, some errors, and it's only shaping up. It's not ready yet. People are and different players are positioning themselves all along the supply chain, but it's shaping up. It's taking time. It's not for tomorrow that everything will be in place. So that's the end of the presentation part. Key takeaways to keep in mind of this webinar, and then we'll switch to the Q&A session. Maybe a quick reminder, our moderator probably wrote it in the chat box, but this presentation will be sent to all the attendees early next week, and you will have the opportunity to ask us questions, to reach out to us to ask us additional questions, of course, if we haven't got time to go through all the questions today. So key takeaways. Hydrogen aircraft can exist. It is technically feasible. It is possible. You need, of course, a long development, long R&D job, and adaptation of the current aircraft to make them able to fly with hydrogen, get the certification. So long way to go. Second takeaway, we want to use hydrogen, of course, to reduce the carbon emissions. So technically, it's achievable to have almost zero carbon emission, neutral carbon aviation with thanks to hydrogen. Knowing that today the current kind of hydrogen produced all around the world is mainly a gray one. It's 98–99% of the current hydrogen production. So more polluting than kerosene and more expensive than kerosene. So it's not ready yet. The goal within the next 10 years is to drive down this 98–99 gray hydrogen to 60–65% only. So that the green hydrogen takes more and more place in the game. Some of the major challenges are around the infrastructure and supply chain, the airport infrastructure and supply chain. We've seen that only for the example of Atlanta Airport, it's a major challenge in terms of electricity production, and additionally some supply chain issues will appear and already appeared as quite important to overcome. So to see hydrogen aviation, all around the world, it's going to be a long way. It can come little by little, small places, but it would be a pity to land in one airport with an aircraft operating hydrogen as a propellant and not being able to refuel because it's not ready. So as for other moves, technological moves, energy transition for cars, for example, you need a big infrastructure and a big move in the infrastructure to support this energy transition. Thank God, we've seen that there are lots of major investment plans in most of the countries all around the world, the biggest countries. So hydrogen aviation will benefit from the scale effect of all these investment plans, and we could expect a boost in the development on hydrogen aviation in the next years, thanks to this investment plan. Production of hydrogen needs electrolysis, and electrolysis, to perform electrolysis, you need electricity. So this electricity increase, if you remember the big figure, and one of the key takeaway, if we want to switch the entire aviation, commercial aviation, to hydrogen, we would need a 35% increase of electricity production. So once again, here it's technically feasible. We have the solutions, different technology to produce electricity. It's well known, but the amount of investments, capex, and numbers of solar panels, nuclear plants, or whatever the technology is such that it will take some years, decades to completely switch to fully hydrogen aviation all around the world. Last takeaway, we've seen that e-fuels are really promising. This synthesized kerosene made out of carbon, hydrogen, and energy, because of their main advantage, which is the fact that they are compatible with current aircraft with the same characteristics as the current kerosene. And if it's well produced with carbon capture in the air, and it's greener than the current kerosene. So despite the cost increase, which is to produce it, which is still a challenge, but some of the challenges that human being is able to overcome, it really has an advantage in terms of green impact, of carbon emission, and it could come in the next 5 to 10 years, and we should see that on some of the aircraft. So 6 takeaways. Thanks for attending this presentation. We're now going to switch to the Q&A session. Frank will pass me a synthesis of the questions you've had, and I will try to answer most of them. Yeah, so no, the first one is it's not about hydrogen, it's about batteries. Basically, the question is, are the batteries viable even for a small aircraft? So you remember the batteries, they have a very low energy density, but this is clearly an option for aircraft, but very small aircraft. So I would answer that for an aircraft of 2 passengers and 500 kilometers operating range, maximum, maybe a bit less, it is doable. It is absolutely doable, but not for commercial aviation with much more passengers and a longer operating range. Next question. Yeah, it's about liquid hydrogen. Yeah, we mentioned liquid hydrogen all along this presentation, and the question is why not considering gaseous hydrogen? So it's a technical issue or answer. Gaseous hydrogen exists, of course. They are the one used by hydrogen cars, for example, but it has a main difference with liquid hydrogen. Gaseous hydrogen, there is a volume impact in comparison with kerosene, which is 7 times higher, bigger than the kerosene. So in a car, it's manageable. Whereas the liquid hydrogen has a volume impact of only 4 times the current kerosene. So you understand that for aircraft application, the most preferred version of hydrogen is the liquefied liquid hydrogen. Next question. Next question. Okay, it's about the evolution of the airport infrastructure. We have a question: is what would be the airport infrastructure evolution, and what would it look like? So we've seen that you need a lot of electricity. You need a lot of changes in the, of course, in the airport infrastructure to be able to store, supply, produce the hydrogen necessary to operate all these hydrogen aircraft in all the major airports. And we do not expect that to be in place before 30 years. Of course, there are a lot of work to do to build these hydrogen plants and bring the liquefaction production means also close to the airport. And there will probably be let's say a smooth transition in the sense that aircraft could operate on demand with hydrogen as a propellant on some airports, while the current kerosene aircraft will still flying and operate in the same airports. So we will have to manage the two technologies for certain time, certain decades probably. We don't see that before 30 years. And we will have to wait probably to the retirement, if we can say it this way, of the current aircraft operating with the kerosene. So knowing that aircraft have a lifetime of some decades, 30 years is the timeline that you can keep in mind to see major switch in the infrastructure of the airport to hydrogen. Yeah, okay. Frank, my moderator, is telling me that we are about to be out of time, or maybe we're already out of time. So thanks for attending this this webinar. We will collect your questions in the chat box, and please send them to us. You have our email address and phone numbers on the page in front of you. You will get reminder the presentation sent to you, a PDF version early next week. It was a pleasure hosting you. I hope you enjoyed it as much as we do, and feel free to reach out for any questions and any challenges you might have around this very exciting topic. Thanks. Have a great day. Have a great one wherever you are.